Hi, uh, good evening, students. Today we are going to discuss about one important application of simultaneous equations model. In previous lectures, we have already discussed the theoretical method of the specification, identification, and estimation of simultaneous equation system models. And today we'll be discussing its application to a small Keynesian macro model. So before that, let me give you a brief background about the macroeconometric models, starting with the contribution of Lawrence Klein. There has been a tradition to construct macroeconometric models which have been very useful for simulation and policy, basically feeding to policy decisions. In India, beginning late 1980s, a macroeconometric model was constructed by Chakrabarty. One before that by Gupta. Then in early 90s, Rangarajan Arif, Narendra Jadhav, Balwant Singh, Dr. Rangarajan and Madhusudan Mahanti. And in IZ, DSC tradition, Pandit Krishnamurti. These are very popular macroeconometric models which were constructed in the Indian context and which were used for policy decisions in central bank like RBI as well as maybe in the ministry. Today we'll be discussing about how to apply simultaneous equation system estimation technique to a small Keynesian model. Okay, actually these macroeconometric model which I was telling, some of them are very big, consisting of hundreds of equations which basically specify the behavioral aspect of various agents of the economy. There are some models like Rangarajan, Arif or Jadhav Singh. These are relatively small models, maybe consisting of 20 to 30 equations. But given this space constraint for us, I will not have even that big model. I may have a small model consisting of 5-7 very important equations, and I'll tell you how it is flexible to expand the model depending on the type and the details of analysis which you want to bring into discussion. So basically the topic for today's discussion is application of simultaneous equation model, a small Keynesian model. So these basically we'll discuss in 3 steps. We'll discuss about the specification of the model, then identification, and then estimation. And reference for today's lecture is the book by Ramu Ramanathan, 2000. This is Introductory Econometrics with Applications. So, although in macroeconomics there have been, lots of developments from the Keynesian days, basically from the general theory. There have been real business cycle model, dynamic, stochastic, general equilibrium models which have become very sophisticated, combining the micro foundations and macroeconomic aspect. But still the Keynesian model, the very simple one, it has some essence of macroeconomic dynamics, and sometimes it is useful to do some simple analysis on the economy. Even you can have a model of 5 to 7 equations, and certain critical aspect of the economy can be captured, and through simulation analysis the impact of certain policy decisions on the economy can be analyzed, even using these small Keynesian models. So after learning the methods of simultaneous equation model, it will be a good experience for you to know how to apply these methods to a small Keynesian model. Coming to first step of model specification, we can think of the Keynesian aggregate demand, which has broadly 4 components: CT, C stands for consumption, I stands for investment, G stands for government expenditure, and X minus IMP, that is export minus import, so net exports, and T basically connotes the time dimension. So basically CT refers to consumption expenditure at time T, and at equilibrium your aggregate income, Y stands for aggregate income, and AD aggregate demand. At equilibrium aggregate consumption, aggregate income is equal to aggregate demand. So that is the the basic Keynesian model to start with. Of course, we will be discussing about the components and their behavior. The traditional Keynesian cross which we generally discuss. So this red line here is the 45-degree line, and all the points on this line stands for the equality between aggregate demand and aggregate income. Aggregate income is on x-axis and aggregate demand is on the y-axis. So I have this line, the consumption expenditure, which is a function of income, basically disposable income, and I have I and G. In this, they are assumed to be autonomous, and net exports is a negative function of income. If I'm assuming export to be exogenous and income increases as income increases, then net exports will be negative. So combining all the components of aggregate demand, we can have this green line which stands for actual aggregate expenditure, and corresponding to the equality, the point here at which it is intersecting the 45-degree line, we get equilibrium income Y and equilibrium aggregate demand AD star, and correspondingly we can also know what is equilibrium consumption expenditure. This is the traditional macroeconomic model as per the Keynesian framework, which we generally learn in our basic macroeconomics. Now coming to various components, it is up to us to what extent we can make the model simpler and to what extent we can make the model more realistic. If you want to make model more realistic, then you have to analyze the behavior of different variables, and if you want to make the model simpler, certain variables we can assume to be exogenous. That way the model can be smaller. So I'll explain as we go on. So here I have the consumption expenditure, the consumption function. Consumption is treated to be function of its past consumption. Given the inertia, current consumption is dependent on past consumption, that is CT is a function of A0, A1, CT minus 1. Then disposable income, current disposable income, and past year's disposable income. Given that disposable income has a lag impact on consumption expenditure, with that logic we are treating this consumption function to be a function of its lag value, current disposable income, and lagged disposable income. So depending on how complicated, how simpler you want to make it, accordingly you can have the flexibility. Now coming to investment function, in the simplest macroeconometric Keynesian model, investment can be treated as exogenous, but I am trying to make it endogenous, where I am treating it as a function of its own lag and interest rate. If somebody goes by accelerator model, they can include YT, aggregate income, as an explanatory variable also. So basically I am trying, there is a flexibility depending on the theoretical underpinning which we believe in, and practicality, we can make the model simpler or more complicated. Now in the government sector, what I am assuming government expenditure is exogenous, okay, but tax I am treating it as a function of income. So basically capital TT is a function of C0 plus C1 YT plus UT. All the UTs, UT or UC, UI, etc. in our model are stochastic variable or random error term. Now coming to the external sector, in external sector again I am assuming X to be exogenous, export to be exogenous, but if you want to make it endogenous, you can make it a function of world income and exchange rate. or it is up to you to what level you can make it complicated, more realistic. And in the external sector, the import is a function of last year's import and disposable income, domestic disposable income, and of course the exchange rate. Okay, and then I'm trying to explain interest rate as a function of money stock and YT. Okay, and if you want, you can even make money stock, money demand as endogenous. Even if you want, you can make exchange rate as endogenous and try to explain it either using a purchasing power parity theory or whatever theory you believe in. So to keep things simpler, as well as to have some realistic dimension, I have tried to construct 5 behavioral equation as I showed to you. The first behavioral equation explains the consumption pattern. The second behavioral equation explains investment behavior. The third one, the tax as a function of income. The fourth one, import as a function of domestic disposable income, exchange rate, and interest rate as a function of money supply and real economic activity, using GDP or YT, aggregate income, as a proxy for real economic activity. And most of the equations, as I showed, we have used the own lag value also as an explanatory variable, basically to take into account the partial adjustment thinking in this. So, and we have 2 identities in this model. The first identity is basically YT, aggregate demand is sum of consumption plus investment plus government expenditure plus net exports. Then another identity which I have, the last one, is disposable income is equal to YT minus TT. So this is basically the specification of our model. So as I told you, depending on your comfort and depending on the type of detailed analysis which you want to undertake, accordingly you can make the model more complicated and more realistic. Our constraint is, given this corona lockdown, I don't have the whiteboard or blackboard to have a detailed discussion. So within these constraints, I'm using a small notebook to explain to you. So that's why I'm trying to make the model as simple as possible, as well to ensure that the essence of the Keynesian macroeconometric model, you should learn how to apply the simultaneous equation estimation techniques. So after specification of the model, the next important step in the simultaneous equation estimation analysis is identifying the equation. We have to identify whether these equations are unidentified, or where they're exactly identified or over-identified. Accordingly, we'll decide the type of estimation technique which we'll be using. So, of course, if a particular equation is unidentified, as we learned, you cannot estimate that equation. We can estimate these equations if either they're exactly identified or over-identified. Now, for identification, we have learned 2 procedures, basically the order condition and the rank condition. The order condition, as we discussed, is the necessary condition, and rank condition is the sufficient condition. So for applying order condition, we need to know the various endogenous variables. We need to distinguish various endogenous variable, exogenous variable, and lagged endogenous variable, so that we can count the number of predetermined variables, number of endogenous variable, and then accordingly, using the order condition, we'll decide whether a particular equation is identified or not. So first, to list out the endogenous variables. In the model, we have these endogenous variable YT, CT, IT, IMPT, TT, and RT, and of course DYT. These are the set of endogenous variables in our model. Then the set of exogenous variables are GT, XT, exchange rate EXR, and money stock. These variables we assume to be exogenous. So if I count, there are total 4 exogenous variable, and lagged endogenous variable are CT minus 1, DYT minus 1, IT minus 1, and IMPT minus 1, again 4. So we have total 4 exogenous, 4 lagged endogenous, so total 8 predetermined variables. Okay, and if you remember, our order condition is we are comparing capital K minus small k with m minus 1 for the particular equation for which we are checking whether that equation is identified or not. Here capital K is total number of predetermined variable in the entire system of equations. So we have basically 5 equations, 2 identities. So in all these equations and identities, total number of predetermined variables, which is basically sum of total number of exogenous variables and total number of lagged endogenous variable. So here we have 4 exogenous variable, 4 lagged endogenous variables. So capital K is 8, that is for the system, and small k is number of predetermined variable in that particular equation for which we are checking whether that equation is identified or not. Okay, and then small m is the number of endogenous variable in that particular equation. So if capital K minus small k, this left hand side, is less than small m minus 1, then that equation is unidentified. So if a particular equation is unidentified, we cannot apply any simultaneous equation estimation technique to that model, that equation. And if capital K minus small k is exactly equal to m minus 1, then equation is exactly identified. Then we can derive unique coefficients for the structural equation from the reduced form equation. And if capital K minus small k is strictly greater than small m minus 1, strictly greater than small m minus 1, then that equation is over identified. That means we can estimate that equation, but there can be more than one value for the coefficients of the structural equation which can be derived from the reduced form equation. So we'll now see how to apply these order conditions for these equations, 5 behavioral equations which we have in our model, and we'll try to estimate. Okay, so now let us come to the first equation, equation 1, which was our the consumption function. So in the consumption function, you look at again what is small k here. Small k is number of exogenous and predetermined variables. So the lagged endogenous variables. So Ct minus 1 is a lagged endogenous variable, so it is a predetermined variable. This is an endogenous variable dyt, but dyt minus 1 is again a lagged endogenous variable, so it is a predetermined variable, right? So in consumption function we have 2 predetermined variables. So small k is equal to 2 in this case. What is small m? Small m is number of endogenous variable. In this there are 2 endogenous variables, Ct and dyt. So for consumption function we have 2 predetermined variables in that equation and 2 endogenous variables. So that's how, as I have noted here, for equation 1, that is the consumption function, small k is equal to 2, small m is equal to 2. These are the 2 predetermined variable and these are the 2 endogenous variables. So capital K already we know it is 8. So you have capital K minus small k, which is 8 minus 2 is equal to 6. Small m minus 1 for this equation is 2 minus 1 is equal to 1. So 6 is strictly greater than 1. So this equation is over identified. Okay. Similarly, you can think of applying the order condition in other equations, and what you will see if you apply this rule to other equations, you will find that in our case all the 5 behavioral equations which we have all are over identified. Okay. So if these equations are over identified, then what we will do, we can apply 2SLS procedure, which we discussed in the last lecture. We cannot apply ILS. We can apply indirect least square or ILS only if the equations are exactly identified. If the equations are exactly identified or over identified, we can apply 2SLS and 3SLS, etc. Now, before I move further, let me come to this point. See here, earlier before learning simultaneous equation system estimation techniques, we were largely confined to a single equation estimation technique. Okay, So in single equation estimation, if you are trying to apply single equation in a multiple regression method to this consumption function, what will be the problem? The problem is in the single equation method, we assume, particularly in order to apply OLS, we assume all the right hand side variables are exogenous variables. Okay, but in this, once you try to understand the linkages across the equations in reality, so basically in reality, the consumption behavior is valid for the economy, investment behavior is valid, that y is equal to AD is equal to C plus I plus G plus X minus Y is valid. So once you try to take into account these interlinkages, then Y, that is income or disposable income, is no more exogenous, because you see Y is equal to AD is equal to C plus I plus G plus X minus M. So whenever there is a change in X, correspondingly there is a change in Y. Your dy is Y minus T. T is tax here, so tax revenue. So if there is a change in Y, there is a change in dy. Okay, so now dy or Y are endogenous, they are no more exogenous. Okay, so in this equation, C as a function of Ct minus 1, dyt and dyt minus 1, this variable is no more exogenous, it is endogenous. So when it is endogenous, there is a strong likelihood that the covariance between this explanatory variable, that is dyt, and the stochastic error term, that is UC here, is no more 0. When the covariance between one of the explanatory variable and stochastic error term is no more 0, then one of these important assumptions of classical linear regression model is violated. Then following Gross Markov theorem, we cannot claim that OLS is best linear unbiased estimator. Okay. In fact, when these simultaneity or endogenous variable appear on the right hand side, then OLS is no more unbiased, it is not even consistent. Okay, so we have a difficulty in applying OLS when there is endogenous variable appearing on the right hand side. So if you go back to our initial discussion on simultaneous equation system, we discussed how to basically apply techniques like ILS, 2SLS, 3SLS, etc. to get rid of the simultaneity bias or the problem of an endogenous variable appearing on right hand side of the equation. Okay. So what we discussed until now, we discussed about the specification of the model, then we discussed about identification of the model by applying order condition. The rank condition is little complicated as we discussed. Let me quickly review what we discussed for rank condition. We discussed that in a simultaneous equation system, if you construct the matrix of the coefficients from this simultaneous equation system by removing the coefficients of the variables, both exogenous and endogenous, both predetermined and endogenous, which are appearing in a particular equation, and then if out of this matrix of such coefficients we can find at least one m minus 1 by m minus 1 matrix which is non-singular, then we'll say the rank condition is satisfied. Let me explain. Say you think of this first equation, which is consumption function. We discussed how to apply order condition and then check whether the equation is identified or not. We applied capital K minus small k and compared that with small m minus 1, and from that we understood that this equation is over identified. Okay, but that is a necessary condition, not a sufficient condition. So necessary condition is that condition without satisfaction of which the equation cannot be identified. Okay, but it is not sufficient means despite this equation being satisfied, possibly the equation may not be identified also unless sufficient condition is met. Okay, so here the sufficient condition is rank condition, as I discussed. So if I test applying rank condition whether this equation is identified or not, what I can do, first I can have I can take all the exogenous variables and endogenous variable, predetermined variables appearing in all the equations in the model. Okay, and corresponding to each variable I can basically write the coefficients from these 5 behavioral equations which we have. Okay, say for example here for the first equation against CT I can write 1, against 1 I can write A0, 1 is the constant. Under CT minus 1 I can write A1, under DYT I can write A2, under DY2 minus 1 I can write A3. Other variables like for under IT I can write 0, under IT minus 1 I can write 0 because these variables are not appearing in this equation. So like that I can have the row of coefficients and zeros for each behavioral equation. We have 5 behavioral equation here, so my capital M is 5 here. Okay, then for checking the identifiability of the consumption function by applying rank condition, what I'll do, I will remove that equation. So we are left with 4 equations now, 4 behavioral equations now. Out of total 5 we remove the first one. Now out of those rest 4, the coefficients of those rest 4 equations which are zeros and A1, A2, A3, B1, B2, C1, etc. Now out of the rest of the coefficients, remove those coefficients which are appearing under the endogenous and predetermined variables which are appearing in equation 1. After leaving out them, rest of the coefficients which are left, if we are basically forming a matrix out of those coefficients, okay, and if there is at least one matrix with m by m, basically m minus 1 cross m minus 1 dimension, okay, which is non-singular, then we'll say the rank condition is satisfied. If we cannot find at least one matrix out of those coefficients which is of m minus 1 by m minus 1 and is non-singular, not singular, that is must be singular, okay, then we'll say the rank condition is not satisfied. Okay, so given that we have many variables in our system, if you apply that procedure you will find that all the equations in our system satisfy the identifiability condition under the rank condition also. So what I'm trying to tell you, both order condition and rank condition suggest that all the 5 behavioral equations in our model are identified, particularly over-identified. So given that these equations are over-identified, we may decide to apply 2SLS or 3SLS estimation procedure to these equations. So the procedure is easy. In the 2SLS procedure, what we are doing, in the first stage we are trying to develop some instruments or try to identify some instruments which will replace the endogenous variable of that particular equation which we are estimating. Say for example, in our consumption function here we have only one endogenous variable which is dyt, and in presence of that we cannot apply OLS technique, so we'll try to find an instrument which will replace dyt. Similarly, if I go to any other equation, say let me come to this input equation. In input equation the endogenous variable dyt again, so we'll try to find an instrument for this. And for interest rate, y is an endogenous variable, we cannot use it in the equation and run OLS, so we'll try to find an instrument for this. So in 2SLS procedure, in the first stage we are trying to develop an instrument for each of the endogenous variable which is appearing on the right hand side of a particular equation which we are estimating. Okay, so going by that, and how to generate this instrument variable or proxy variable, we'll be basically using all other predetermined variables on the system to run a regression on this variable on the left hand side and try to get the estimated value which will be used as an instrument. For example, what we are doing for finding an instrument for dyt, we are running a regression of dyt on all the predetermined variables. We have gt, we have xt, we have exchange rate, we have mt, ct minus 1, dyt minus 1, it minus 1, imp, t minus 1. We have 8 predetermined variables. So in the first stage we'll run a regression of dyt on all those 8 predetermined variables, and from this regression we'll get the estimated value of dyt, which we are writing as dyt star, and this dyt star now becomes a proxy for dyt, and this will be using in the second stage as a instrument for the dyt. So in the second stage what I'll do, I'll run that original behavioral equation for consumption function. Ct is equal to a0 plus a1 ct minus 1 a2 dyt star. Earlier we had in our original model dyt, we are replacing dyt with dyt star, so this is the instrument we are using, and again rest of the things remains the same. So if I had two endogenous variable, correspondingly for those two endogenous variable I would have generated proxies or instrument variable using the same procedure, okay, and in the second stage I would have ran the regression of the original equation by replacing those endogenous variable with the corresponding instruments or corresponding proxies, okay. So that is the second stage. Now this is no more endogenous variable, so we basically got rid of the problem of endogeneity now by using the instrument. Now, as I discussed earlier, applying 2SLS is fine. You can estimate these equations in the simultaneous equation system where you have an endogenous variable on the right hand side, but still we have some scope to improve the 2SLS coefficients. This way of estimating all the individual equation we can apply to equation 2, equation 3, equation 4, equation 5, etc. That completes the 2SLS procedure. But we can improve this 2SLS procedure by adopting 3SLS procedure, where the first two stages remains the same. In the 2SLS, as we know, it is two-stage least square procedure. So now in the third stage, what we can do, we can try to find the interlinkages between all the stochastic error terms. The stochastic error term in the consumption function is UC, for investment UI, for imports UIMP, for interest rate UR, etc. These are the stochastic disturbance term in our, or error terms in our respective behavioral equations. If we can find the variance covariance matrix of these estimated stochastic error terms, then by using these variance covariance matrix we can suitably adjust the estimated structural coefficients which we obtain in the second stage of 2SLS, and then we can get the estimated coefficients of these structural equations in the third stage. So that is the 3SLS procedure, okay. So this is all about how to apply the simultaneous equation system estimation techniques which we have learnt in this module to a small Keynesian model. I think we can do some hands-on on this, and you can try to modify the model as per your comfort, and using more theoretical insights to improve such models and make it, you can have a more realistic, more complicated model which will be more suitable, or maybe which will be more suitable for macroeconomic analysis which you want to undertake, okay. So to repeat, if you have some doubts on this, you can get back to me, and as I said, you use the reference the introductory econometrics with applications by Ramu Ramanathan for this lecture. And with this, our module 4 is completed. The simultaneous equation estimation techniques is completed, and with the next lecture we'll start with dummy variable estimation technique. Okay, all the best. Thank you.